Example 10, it says a company makes a car with 11 upgrade options. So that's the number of items that we have. Okay, it says how many different versions of this car can this company produce? Assume that each upgrade option is independent of other options. Okay, so how many upgrades can we have? Well, if there's 11 items, what they're really asking is how many subsets are there? Okay, that's what they want to know. And here we have 11 distinct things, so we would have 2 to the n, which in this case is 2 to the 11. Go ahead and put that into your calculator. 2 to the 11, I'm getting 2048. That's how many distinct different versions there are. So it says how many different versions, and I'm going to answer 2048 versions. Any real-world problems, you do want to try to label your answer. Okay, so it says, what is the minimum number of upgrade options the company must provide if it wishes at least 8,000 different versions of the car? Well, I know 11 is 2048, and that's not enough. So let's look at 12 options. I'm just going to start guessing. 13 options. Let's see what happens here. So if it's 12 options, let's do 2 to the 12th and see what we would get. So do 2 to the 12th in your calculator. And I get 4096. So that's not enough. We need 8,000, right? So let's look at 13 options. So that would be 2 to the 13th. Put 2 to the 13th in your calculator. See what you get. That's 8192. And is that enough? Well, that is, because you only needed 8,000. So what does that mean? It means you need at least 13 options. If you have 13 options or more, you can say you have at least 8,000 different versions of this car. Okay. This last one, there's no math to do. I just love messing with my students in class at this one. It's called the Barber's Paradox, and it came from something else and turned into this. In fact, let's read this. It says, some problems that concern sets have led to paradoxes. For instance, in 1902, the mathematician Bertrand Russell developed the following paradox. Russell's paradox has been popularized as follows. So this is an easier understandable, and it's not really understandable, version of the paradox. It says, the town barber shaves all males who do not shave themselves, and he shaves only those males. So he shaves all people who do not shave, and he shaves only those people. So it says the town barber is a male who shaves. So who shaves the barber? So read that again. The town barber shaves all males who do not shave themselves and shaves only those males. The town barber is a male who shaves. Who shaves the barber? So what's the issue? If he shaved himself, that would be a contradiction to this first sentence, because the first sentence says he only shaves people who don't shave themselves. So that means he can't shave himself. But if he doesn't shave himself, that's a contradiction to the second sentence that says the barber shaves. So you have a contradiction to the first sentence or a contradiction to the second sentence, depending on whether you say he shaves himself or whether he doesn't shave himself. So there's no correct answer. There's a contradiction in either decision, whether he shaves himself or not. That's called a paradox. And when you get into these logical arguments, you can get into these fun problems where there's these paradoxes where there's actually no correct answer. Pretty cool.